Buckle up, cosmic pioneers, as we embark on a thrilling odyssey into astrobiology, the groundbreaking science unraveling the secrets of life beyond our blue planet. Welcome to a mesmerizing journey where we'll explore the origins of life, hunt for hidden oceans on distant moons, and peer into alien atmospheres, all in the quest to answer one of humanity's most profound questions: are we alone in the universe? What clues hide in the icy depths of Europa or the hazy skies of Titan? How are we sniffing out signs of life on worlds light years away? And what might alien life look like if we find it? Get ready for an epic adventure packed with cutting-edge discoveries and mind-bending possibilities that will keep you hooked from start to finish. Let's dive into the captivating world of astrobiology together. Imagine standing on the shore of an ancient Earth, billions of years ago, as lightning crackles across a stormy sky and volcanic vents bubble with primordial chemistry. From this chaotic cradle, life emerged, a single spark that evolved into the incredible diversity we see today, from microscopic bacteria to towering redwoods and intelligent humans. Astrobiology is the interdisciplinary science that seeks to understand how life began here and whether it could exist elsewhere in the cosmos. It blends biology, chemistry, physics, geology, and astronomy to probe the potential for life beyond Earth, from microbial organisms in subsurface oceans to advanced civilizations broadcasting signals across the stars. This field isn't just about finding aliens, it's about comprehending the conditions that make life possible, the resilience of living systems, and our place in the grand tapestry of the universe. As we venture deeper, you'll discover how astrobiology is rewriting our story, one cosmic clue at a time. Doesn't that make you wonder what secrets the stars are hiding? The roots of astrobiology stretch back to ancient times, when philosophers like Epicurus and Lucretius speculated about multiple worlds teeming with life. But the modern field took shape in the 20th century, fueled by advances in space exploration and biology. In 1953, Stanley Miller and Harold Urey's famous experiment simulated Earth's early atmosphere, zapping a mix of methane, ammonia, hydrogen, and water with electricity to produce amino acids, the building blocks of proteins. This sparked the idea that life's chemistry could arise naturally, not just on Earth but anywhere with similar conditions. NASA formalized astrobiology in 1995, establishing the Astrobiology Institute to coordinate research. Today, astrobiology encompasses everything from studying extremophiles, organisms thriving in Earth's harshest environments, to analyzing exoplanet atmospheres with telescopes like the James Webb Space Telescope. It's a field that's grown exponentially, with missions probing our solar system and beyond, all driven by the tantalizing possibility that life is not an earthly anomaly but a cosmic commonplace. At its core, astrobiology asks three big questions: how does life begin and evolve? Does life exist elsewhere in the universe? And how can we detect it? To tackle the first, scientists study abiogenesis, the transition from non-living chemistry to self-replicating life. On Earth, this likely happened around 3.8 to 4 billion years ago, soon after the planet cooled from its molten birth. Theories abound. The primordial soup hypothesis suggests organic molecules formed in shallow ponds or oceans, energized by lightning or UV light. The hydrothermal vent theory, championed by researchers like Nick Lane, proposes that life started at deep-sea vents, where hot, mineral-rich water meets cold ocean, creating chemical gradients that power early metabolism. Alkaline vents, with their porous rock structures, could have acted as natural cell membranes, concentrating molecules for reactions. RNA world hypothesis posits that RNA, capable of storing information and catalyzing reactions, was life's first molecule, evolving before DNA and proteins. Experiments like those at the Scripps Institution have synthesized RNA precursors under vent-like conditions, bolstering this idea. Panspermia adds a twist: life or its precursors might have arrived on meteorites, as evidenced by amino acids in the Murchison meteorite, which fell in 1969 and contains over 100 organic compounds. If abiogenesis is common, life could spark on any world with water, energy, and organics. But if rare, Earth might be a lonely outpost. What if the key to life's recipe is universal? The search for life starts in our solar system, a laboratory of diverse worlds. Mars, our rusty neighbor, tops the list with its ancient water-carved valleys, like Valles Marineris, and sediment layers in craters like Gale, explored by Curiosity since 2012. Perseverance, landing in Jezero crater in 2021, has collected over 20 rock samples, including from a dried river delta, for the Mars Sample Return mission, planned for the 2030s. These could hold fossilized microbes or organic molecules. Methane plumes, varying seasonally and detected by Curiosity and orbiters like Trace Gas Orbiter, Intrigue. On Earth, methane comes from geology or biology, but Mars' source remains debated. Subsurface briny water, stable at low temperatures, could host extremophiles, as suggested by radar data from Mars Express in 2018 showing liquid lakes under the South Pole. Radiation and perchlorates make the surface hostile, but underground refuges might preserve life from Mars' wetter past, 3 to 4 billion years ago. As of 2025, Perseverance's ongoing analyses and the Tianwen-1 rover's findings continue to build the case. Could a Martian microbe rewrite our history? Jupiter's moon Europa is another prime target, with its smooth ice shell hiding a global ocean of salty water, estimated at 100 kilometers deep, more than twice Earth's ocean volume. Galileo's 1990s flybys detected a magnetic field induced by saltwater, and Hubble spotted water plumes in 2016, erupting from cracks like geysers. These plumes, containing salts and organics, offer a way to sample the ocean without drilling. Tidal heating from Jupiter's gravity flexes Europa, powering potential hydrothermal vents on the seafloor, similar to Earth's black smokers where life thrives without sunlight, fueled by chemical energy. Europa Clipper, launching in October 2024 and arriving in 2030, will make 49 flybys, using radar to map the ice and ocean, spectrometers to analyze plumes, and instruments to hunt for organics. If vents exist, they could host chemosynthetic bacteria, a parallel biosphere. Radiation from Jupiter's belts bombards the surface, but the ocean's depth shields it. As of 2025, preparations for Clipper and ground-based observations build excitement. Imagine finding life in Europa's hidden sea. What would it teach us about life's universality? Saturn's Enceladus is equally enticing, with its South Pole geysers spewing water, ice, salts, and organics hundreds of kilometers into space. Cassini's 2005 to 2017 mission flew through these plumes, detecting hydrogen gas, a potential energy source for microbes, and complex hydrocarbons like propane. The ocean, 30 to 40 kilometers deep under 20 kilometers of ice, is kept warm by tidal friction, with rocky core vents possibly providing minerals for life. Silica nanoparticles in the plumes suggest hydrothermal activity at over 90 degrees Celsius, ideal for thermophiles. Proposals like Enceladus Life Finder aim to sample plumes for biosignatures, amino acids, lipids, or chiral molecules favoring left-handedness like Earth's life. In 2025, post-Cassini analyses and Dragonfly's Titan focus keep Enceladus in view. Could these geysers hold the key to Saturnian life? Titan, Saturn's largest moon, offers a different allure with its thick nitrogen atmosphere and surface lakes of methane and ethane, the only stable liquids besides Earth's water. Cassini-Huygens' 2005 landing revealed dunes of organics, rivers carving valleys, and a prebiotic chemistry rich in tholins, complex hydrocarbons formed by UV light. Titan's -179 degrees Celsius surface is cold, but subsurface oceans of water ammonia could host life using methane as a solvent, a hypothetical, methanogen, biology. Dragonfly, launching in 2028 and arriving in 2034, will hop across Titan's terrain, analyzing chemistry for life precursors. In 2025, mission prep and lab simulations advance our understanding. Titan challenges our water-centric view. What if life swims in hydrocarbon seas? Venus, our hellish twin, surprises with potential. Once possibly habitable with oceans, Venus now boils at 464 degrees Celsius under 92 atmospheres of CO2. But 2020's phosphine detection in clouds, a potential biosignature, though debated as sulfur dioxide, revived interest. Clouds at 50 to 60 kilometers altitude are temperate, with sulfuric acid droplets that Earth extremophiles might tolerate. Missions like Da Vinci, launching 2029, will probe the atmosphere, and Veritas will map the surface. In 2025, reanalysis of Pioneer and Venera data fuels debate. Could floating microbes survive Venus skies? Beyond our system, exoplanets expand the search. Kepler's transit method, dimming starlight as planets cross, found thousands, with TESS continuing the hunt for nearby worlds. Habitable candidates like Teegarden B, in a red dwarf zone 12 light-years away, or LHS 1140b, a super-Earth with potential water, excite. JWST's 2025 observations of TRAPPIST-1 planets analyze atmospheres for water vapor, CO2, or ozone. Biosignatures like oxygen with methane suggest life, as they react without replenishment. Challenges: red dwarf flares strip atmospheres, as seen in Proxima b models. Future telescopes like the Habitable Worlds Observatory will image Earth twins. As of 2025, JWST's data on K2-18b's Hycean world, ocean covered with hydrogen atmosphere, hints at dimethyl sulfide, a algal byproduct, though unconfirmed. Could these distant dots hold life spark? SETI complements the hunt, listening for intelligence. From Arecibo's 1974 message to Messier 13 to breakthrough listen scans, we seek narrowband radio or laser signals. The water hole frequency, 1420 to 1660 MHz, is quiet for noise, ideal for contact. Technosignatures like Dyson swarms, star-encompassing solar panels, would dim stars irregularly, as searched in Kepler data. No luck yet, but the square-kilometer array, phased in 2025, will boost sensitivity. The Fermi paradox looms. Where are they? Rare intelligence or self-destruction? SETI's optimism endures. Challenges abound. Biosignatures mimic geology, Venus phosphine debate shows this. Distances limit probes, Voyager's 45 years reached interstellar space, but Alpha Centauri is 4 light-years away. Contamination risks forward and back, protecting alien ecosystems or false positives. Funding and politics slow missions. Yet, astrobiology thrives, with 2025's NASA update and conferences like UpGradCon advancing collaboration. The future gleams. Europa Clipper's 2030 arrival, Dragonfly's Titan hops, Mars sample returns analyses, 2025 sees progress. JWST's Exoplanet Spectra, Ariel's 2029 launch surveying 1,000 atmospheres. Private ventures like Breakthrough Starshot's LightSail probes to Proxima. Biosignature databases refine searches. If we find life, it transforms biology, philosophy, religion, proof we're not alone. What does astrobiology mean for us? It connects our origins to the stars, seeking kin in the void. Your atoms, forged in supernovae, link to this quest. From Miller's flask to JWST's gaze, curiosity propels us. We're astrobiologists at heart, pondering life's reach. As we near the end, let's gaze ahead. Astrobiology, science of life beyond Earth, unveils cosmic possibilities, from Martian microbes to exoplanet biospheres. New missions, data, and dreams will illuminate it. What lives out there? How will discovery change us? The universe beckons, full of wonder. What questions stir your mind? Thank you for joining me on this epic dive into astrobiology, the science of life beyond Earth. I hope your curiosity blazes. If you love this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about astrobiology? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Pioneers.